Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this green shape that is inside square ABCD. In the second question, we'll find out the area of this green shape that is inside quarter circle AOB. So let's start with the first question. In the drawing, we have square ABCD. This is angle PQC, that is a right angle. This is line segment PQ, this equals to 2 units in its length. This is line segment QC, this equals to 4 units in its length. Again, our mission is to find out the area of this green shape. So first of all, we know that all the angles inside the square are right angles. So those 4 angles, they are all right angles. So this is a right angle. This is a right angle. This is also a right angle. And this is a right angle. And we also know that all the sides of any square are equal to each other. So we define one side of this square as A, and so all the other sides must be also equal to A. So this is side AB. Of square ABCD, and the length of side AB is equal to A units according to our definition. Likewise, side AD, the length of side AD is also A units. Side BC, this is side BC, this is equal to A units in its length, and side BC also equal to A units in its length. We define this line segment QB as X. So what is the length of AQ? AQ equals to AB minus QB. Again, AQ equals to AB minus QB. So write it down. AQ equals to AB minus QB. So AQ in total equals to AB, that is A, minus QB, that is X. So in total AQ equals to A minus X units in its length. AQ equals to A minus X. We define this angle QCB as alpha. So in the right angle QBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. AB is one side of square ABCD, and therefore it is absolutely a straight line. So if we focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is 90 degrees minus alpha. This is a right angle, and plus this missing angle. In total, the sum of those 3 angles must be equal to 180 degrees according to rule 3. Therefore, this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees. 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles of this side of the straight line AB at point Q according to rule 3. Okay, so this missing angle must be equal to alpha. So in the right angle APQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I'll copy this right triangle APQ and this right triangle QBC in the new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are going from the original drawing. This is triangle APQ, this is the right triangle QBC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle APQ, and the right triangle APQ, and it is equal to this angle BQC, and the right triangle QBC. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PAQ in the right triangle APQ, and it is equal to this angle, this is actually angle QBC in the right triangle QBC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So actually, this is angle AQP in the right triangle APQ, and it is equal to this angle, this is actually angle QCB in the right triangle QBC. They are both equal to alpha and therefore they are equal to each other. So if we found out that all the triangles in this right triangle APQ are correspondingly equal to all the triangles in this right triangle QBC, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it now. So if we found out that the right triangle APQ is similar, this is the sign of similar to the right triangle QBC according to angle similarity rule. from the fact that those two right triangles are similar to each other, we will derive from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP, this right triangle APQ, over side QB in this right triangle QBC is equal to side AQ in this right triangle APQ over side BC in this right triangle QBC, and it is also side PQ, this right triangle APQ, or side QC in this right triangle QBC. So repeat again. We derive that side AP, the right triangle APQ, or side QB, the right triangle QBC is equal to side AQ, the right triangle APQ, or side BC, the right triangle QBC, and also equals to side PQ in the right triangle APQ, or side QC in the right triangle QBC. AP is the missing side, so we will do it as it is. Over QB. QB is X, and it is equal to AQ. AQ is A minus X over BC. BC is A, and it is also equal to PQ, that is 2, over QC, that is 3. So in total, according to equation 1, we can find out that AP over X equals to A minus X over A, and it is also equal to 2/3. Those two expressions are equal to each other, so we create equation 1 from those two expressions that are equal to each other. That is to say, according to equation 1, AP over X equals to 2/3. So write it down. AP over X equals to 2/3. Here we multiply this equation 1 by X, and finally get that according to this equation 1, AP equals to 2/3 X. Those two expressions are equal to each other, so we get equation 2 from those two expressions that are equal to each other. So according to equation 2, we get that A minus X over A equals to 2/3. So I write it down. So according to equation 2, A minus X over A equals to 2/3. Here we cross multiply this equation 2, and get that according to this equation 2, 3 times A minus X equals to 2A. We'll open the brackets on this side of this equation 2, and get that 3A minus 3X equals to 2A. Here we subtract 2a from this equation 2. And finally get that 3a minus 2a is a, so a minus 3x equals to 0. Here we add 3x to this equation 2, and finally get that according to this equation 2, a equals to 3x. A equals to 3x according to equation 2. In the next step, I'll copy this right triangle QBC in the new page and we'll implement the Pythagoras theorem on this right triangle, triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a evaluation for Pythagoras theorem. So here this is the right triangle QBC, it is according to the original drawing. According to the Pythagoras theorem, in this right triangle QBC, QC squared, that is the square of the hypotenuse, equals to QB squared plus BC squared. So I write it down, this will be equation 3. So QC squared equals to QB squared plus BC squared. The hypotenuse QC is 3, therefore QC squared is 3 squared, that is 9. And it is equal to QB squared, QB is x, therefore QB squared is x squared plus BC squared. BC is a, therefore BC squared is a squared. So in total, according to equation 3, we actually found out that 9 equals to x squared plus a squared. This is according to equation 3, while according to equation 2, we have already found out that a equals to 3x. According to equation 2, a equals to 3x. If a equals to 3x, it means that a squared equals to 3x squared. Therefore, we can substitute a squared in this equation 3 by 3x squared for this equation 2. We'll do it now, and we get that according to equation 3, according to equation 3, 9 equals to x squared plus a squared. and a squared according to equation 2 is 3x squared. So in total we can find out that 9 equals to x squared plus 3x squared. So 3x squared is 9x squared. So in total we can find out that 9 equals to x squared plus 9x squared. X squared plus 9x squared is 10x squared. So in total we found out that 9 equals to 10x squared. Here we divide this equation 3 by 10, and finally get that according to this equation 3, x squared equals to 9 tenths. Here we take out of this equation, and we get that according to equation 3, x equals to the square root of 9, that is 3, or square root of 10. So in total we found out that x equals to 3 over square root of 10 units in its length. We already found out that according to equation 2, a equals to 3x. So a equals to 3 times x, and x is 3 over square root of 10. And total a equals to 3 times 3 is 9 over square root of 10. So in total we found out that a equals to 9 over square root of 10 units in its length. This equals to a, and a equals to 9 over square root of 10 units in its length. According to equation 1, we already found out that AP equals to 2/3 x. It again, according to equation 1, AP equals to 2/3 x. So AP equals to 2/3 times x, and x is 3 over square root of 10. So in total we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. We left only with 2 over square root of 10. So in total we should find out that AP equals to 2 over square root of 10 units in its length. So here this is 9/7 AP, that is equal to 2 over square root of 10 units in its length. What is the length of this 9/7 PD? For the moment it is very easy to see that PD equals to AD minus AP. Okay, again, for the moment it is very easy to see that PD equals to AD minus AP. So PD equals to AD. AD is A, and A equals to 9 over square root of 10 minus AP. AP equals to 2 over square root of 10. So in total we found out that PD equals to 9 over square root of 10 minus 2 over square root of 10 is 7 over square root of 10 units in its length. So if I found out that this 9/7 PD equals to 7 over square root of 10 units in its length. In the next step, we join points P and C together by a straight line. By joining points P and C, we get two right angles. The right triangle PDC and the right right triangle PQC. Actually, because of the fact that this grain shape consists of two right triangles, it means that the area of the green shape must be equal to the sum of the areas of the two right triangles that it consists of. That is to say, the area of the green shape must be equal to the area of this green right triangle PDC plus the area of this green right triangle PQC. So I write it down. The area of the green shape in total is equal to the sum of the areas of the two components that it consists of. That is to say, it is equal to the area of the green right triangle PDC plus the area of this green right triangle PQC. So if it again, I should find out the area that we are looking for in this question, the area of the green shape, is equal to the sum of the areas of the two components that the green shape consists of. That is to say, it is equal to the area of the right green triangle PDC plus the area of this green right triangle PQC. What is the area of the green right triangle PDC? The area of the green right triangle PDC equals to the base of the triangle that is PD times the height that is DC over 2 plus the area of this green right triangle PQC. What is the area of the green right triangle? This green right triangle PQC, it is equal to the base that is PQ times the height that is QC divided by 2. So if it again, if we found out the right triangle PDC equals to the base PC times the height DC over 2 plus the area of the right triangle PQC, this is equals to the base that is PQ times the height that is QC over 2. PD equals to 7 over square root of 10 times DC. DC equals to 9 over square root of 10 divided by 2. And again, if we found out that in total the area of the right triangle PDC equals to 7 over square root of 10 times 9 over square root of 10 divided by 2 plus the area of the right triangle PQC that equals to PQ that is 2 times QC that is 3 divided by 2. And again, the area of the right triangle PQC equals to 2 times 3 over 2, 2 over 2 is 1, so left only with 3. So in total, there are the green shape is equal to, what is the value of this expression? We have here 7 times 9 is 63 over square root of 10 times square root of 10 is 10 divided by 2 plus 3. 63 over 10 over 2 equals to 63 over 10 times 2 plus 3. So it is 63 over 10 times 2 is 20. So it is 63 over 20 plus 3. So here we multiply 3 by 20 and then we divide this by 20 in order to come factor with this number. So in total, the numerator will have 63 plus 3 times 20 is 60 divided by 20. 63 plus 60 is 123 divided by 20. 123 over 20 is 6.15 square units. And that is the answer to the question. Repeat again. Actually, we found out that the area of this green shape equals to either 123 or 20 square units. So in terms of numbers, the area of this green shape equals to 6.15 square units. We finished with the first question. In the next step, I'll present you the second question and we will solve the second question of this lecture. In this second question, our mission is to find out the area of this green shape. So in the drawing, we have quarter circle AOB. It is given us the question that those three angles, they are all right angles. Also, we know that OB equals to 5 units in its length. That is to say, the radius of this quarter circle is 5. In addition, we know that arc AP equals to arc PQ equals to arc QB. That is to say, that the arcs are equal to each other in their lengths. And our mission is to find out the area of this green shape. So first of all, we join points O and P together by straight line. We also join points O and Q together by straight line. Because of the fact that arc AP equals to arc PQ equals to arc QB, we can implement the rule 20. So I'll get quickly on rule 20. According to rule 20, in front of equal arcs, there are equal center angles. So in the drawing, we have a circle. And we know that arc AB equals to arc CD in its length. And according to this rule 20, the center angles that are located in front of those two equal arcs are also equal to each other. In front of this arc AB, we have this center angle alpha. In front of this arc CD, we have this center angle beta. And according to this rule 20, those two center angles are equal to each other because of the fact that they are located in front of those two equal arcs AB and CD. Okay. So you can actually implement rule 20 in our drawing. Why? Because we know that arc AP equals to arc PQ equals to arc QB. In front of this arc AP, we have center angle AOP. This is a center angle AOP. In front of this arc PQ, we have center angle POQ. This is center angle POQ. And finally, in front of this arc QB, we have center angle QOB. So actually, those three center angles AOP, POQ, and QOB are equal to each other because of the fact that they are located in front of equal arcs. So all those three center angles are equal to each other. So if we define the size of this center angle AOP as x, then the size of this center angle POQ must be also equal to x, and the size of this center angle QOB must be also equal to x degrees in its size. Okay, according to rule 20, of course. X plus x plus x is 3x. It's very easy to see from the drawing that the sum of those three angles gives us the big angle AOB. That is to say, angle AOB equals to 3x from one side, but from the other side, angle AOB equals to also to 90 degrees according to what is given as a question. Therefore, we conclude that 90 degrees equals to 3x. 90 degrees equals to 3x. Here we divide this equation by 3 and finally get that x, everything angle x, is equal to 90 degrees over 3 is 30 degrees. So third angle AOP that is equal to x is equal to 30 degrees in size. Third angle POQ that is also equal to x, it is also equal to 30 degrees in its size. And finally, third angle QOB is equal to x is also equal to 30 degrees in its size. So in the right triangle MPO, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this third incident angle must be equal to 60 degrees in its size. According to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. 60 degrees plus 30 degrees is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the right triangle NOQ, this angle NOQ equals to 30 degrees plus 30 degrees, that is 60 degrees. This angle equals to 90 degrees, and therefore this firmness angle must be equal to 30 degrees in its size, according to the same rule that states that the sum of the angles in any triangle is equal to 180 degrees. OP is the radius of this circle, that is equal to 5. OQ is also the radius of the circle, that is equal to 5. In the next step, I'll copy the right triangle MOP and this right triangle NOQ in a new page, and we will prove that those two right triangles can go into each other according to angle side angle rule. So showing those are the two right triangles, MPO and NQO, that are going from the original drawing. So why those two right triangles can go into each other? First of all, those two angles are both equal to 60 degrees and therefore they are equal to each other. So actually this is angle MPO. In the right triangle MPO, and it is equal to this angle, that is actually angle NOQ. In the right triangle NQO. They are both equal to 60 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 30 degrees and therefore they are equal to each other. Actually, this is angle MOP in the right triangle MPO, and it is equal to this angle, that is actually angle NQO in the right triangle NQO. They are both equal to 30 degrees and therefore they are equal to each other. And finally, side PO in the right triangle MPO equals to side QO in the right triangle NQO. They are both the radii of the circle and therefore they are equal to each other. So PO equals to QO equals to R equals to 5. So actually prove that those two angles and the side that is included between those two angles, it is side PO in the right triangle MPO, are correspondingly equal to those two angles, and the side that is included between those two angles, it is side QO in the right triangle NQO, and therefore those two right triangles can go into each other according to angle side angle rule. So I write it down. Actually prove that the right triangle MPO congruent, this is the side of congruent to the right triangle NQO according to angle side angle rule. And for the fact that those two right triangles can go into each other, we will derive that they have also the same areas. Why? Because any triangles that can go into each other, they must have also the same areas. So that is to say, the area of this triangle MPO is equal to the area of this right triangle NQO. So I write it down. The area of this right triangle MPO is equal to the area of this right triangle NQO. And again, the area of the right triangle MPO is equal to the area of the right triangle NQO, because of the fact that those two right triangles can go into each other. So, because of the fact that the right triangle MPO contains two components, that is to say, you can define this point as point S. So the right triangle MPO consists of quadrilateral, the green quadrilateral MNSP, and it also consists of this right triangle NSO. And therefore the area of this right triangle MPO must be equal to the sum of the two components that it consists of. That is to say, it must be equal to the area of this green quadrilateral MNSP plus the area of this right triangle NSO. So I write it down. The area of the right triangle MPO is equal to the area of this green quadrilateral MNSP plus the area of this triangle, right triangle NSO. So once again, the right triangle NPO is equal to the sum of the areas of the two components that it consists of. That is to say, is equal to the area of the green quadrilateral MNSP plus the area of the right triangle NSO. And according to equation 1, the area of triangle NPO is equal to the area of triangle NQO. So this is the right triangle NQO. It is very easy to see from the drawing that this right triangle NQO consists of two small triangles. Consists of this small right triangle NSO, and it also consists of this triangle SQO. And therefore, the big right triangle NQO must be equal to the sum of the two areas of the two components that it consists of. This is to say it must be equal to the area of this right triangle NSO plus the area of this triangle SQO. So I write it down. The area of the right triangle NQO equals to the area of the small right triangle NSO plus the area of this triangle OSQ. So if it again, I should find out that the area of quadrilateral MNSP plus the area of the right triangle NSO is equal to the area of the right triangle NSO plus the area of the triangle SQO. We have in this equation 1 the area of triangle NSO on both sides of the equation. So we subtract the area of the right triangle NSO on both sides of the equation. So the area of the right triangle NSO will get cancelled, and then afterly with the area of the green shape MNSP that is equal to the area of triangle OSQ. Okay. So if we found out that the area of this quadrilateral MNSP is equal to the area of this triangle OSQ. Our mission is to find out the area of this green shape. So what is the area of the green shape? For the drawing, it is very easy to see that the area of the green shape equals to the area of the green quadrilateral MNSP plus the area of this green shape PQS. So write it down. The area of the green shape equals to the area of the green quadrilateral MNSP plus the area of this small green shape PSQ. So repeat again, if we found out that the area of the green shape in total is equal to the area of the green quadrilateral MNSP plus the area of the small green shape PSQ. But we already found out that the area of the green quadrilateral MNSP equals to the area of triangle OSQ. Therefore, you can substitute the area of the quadrilateral MNSP by the area of triangle OSQ. We'll do it now, and we get actually that the area of the green shape in total equals to the area of quadrilateral MNSP. We substitute the area of quadrilateral MNSP by the area of triangle OSQ plus the area of the green small shape PSQ. So repeat again, I should have found out the area of this green shape, that is the area that we are looking for in this question, is equal to the area of triangle OSQ, this one triangle OSQ, plus the area of this green small shape PSQ. But for the drawing it is very easy to see that the area of triangle, the small shape PSQ, plus the area of this white triangle OSQ is equal exactly to the area of sector POQ. Why? Because sector POQ consists of the small green shape P, this small green shape PSQ, and it consists of also this white triangle OSQ. So we found out that the area of the green small shape, the area of the small shape PSQ plus the area of the white triangle OSQ is equal to the area of sector OPQ. So here the rounded line above OPQ is the sign for a sector, means the area of sector OPQ. But what is the area of the sector OPQ? The area of this sector OPQ is equal to pi r square. That is the area of the circle that contains this sector OPQ times the angle between the legs of the sector. This is 30 degrees. 30 degrees is the angle between the legs of this sector OPQ. So it is 30 degrees over 360 degrees. So in total we found out that the area of the green shape is equal to the area of sector OPQ. And the area of sector OPQ equals to pi r square times 30 degrees over 360 degrees. R is the radius of this quarter circle, that is equal to 5, therefore r square is 5 squared, it is 25. So in total, pi r square is 25 pi. 30 degrees over 360 degrees is 1 over 12. And 25 pi over 12 is 6.545 square units. So repeat again, we should have found out that the area that we are looking for in this question, that is the area of this green shape, equals to either 25 pi over 12 square units, so in terms of numbers, the area of this green shape equals to 6.545 square units. So we finished with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this green shape. So in the drawing, we have square ABCD. This is angle PQC, that is the right angle. This is line 7PQ, this is equals to 2 units in length. This is line 7QC, this is equals to 4 units in length. Again, our mission is to find out the area of this green shape. So first of all, ABCD is a square, so those 4 angles, they are all right angles. We defined one side of this square ABCD as A, therefore AD equals to DC equals to CB equals to BA equals to A. All the sides of this square ABCD is equal to A according to our definition. In addition, we define this line segment QB as x. What is the length of AQ? From the lower integrality to say that AQ equals to AB minus QB. AQ equals to AB minus QB. So AQ equals to AB, that is A, minus QB, that is x. So in total, AQ equals to A minus x. We define this angle QCB as alpha. So in the right triangle QBC, this angle equals to alpha, this angle equals to 90 degrees. And therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, actually, we know that AB is one side of square ABCD. So AB is a side of a square, it is absolutely a straight line. So if we focus on this side, on the left side of this straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is 90 degrees minus alpha, this is the right angle, plus this missing angle. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Therefore, this first missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles on this side of the straight line AB at point Q according to rule 3. So the missing angle must be equal to alpha. In the right angle AQP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in the triangle is equal to 180 degrees. In the next step, I copied this right triangle APQ and this right triangle QBC in a new page, and we proved that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles APQ and QBC that are coming from the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So actually found out that all the triangles in this right triangle APQ are corresponding equal to all the triangles in this right triangle QBC, and therefore those two right triangles are similar to each other according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP in the right triangle APQ or side QB in the right triangle QBC is equal to side AQ in the right triangle APQ or side BC in the right triangle QBC, and it is also equal to side PQ in the right triangle APQ over side QC in the right triangle QBC. AP is the missing side, so we leave it as it is. QB is x, AQ is a minus x, BC is a, PQ is 2, and QC is 3. So in total, according to equation 1, we should found out that AP over x equals to a minus x over a, and it is also equal to 2/3. So those two sides are equal to each other, so we created equation 1 from those two sides that are equal to each other. So according to equation 1, we should found out that AP over x equals to 2/3. Here we multiply this equation 1 by x, and finally found out that AP equals to 2/3 x. Likewise, those two sides are also equal to each other, or those two expressions are equal to each other. Therefore, we created equation 2 from those two expressions that are equal to each other. So according to equation 2, a minus x over a equals to 2/3. Here we cross multiply this equation 2, and finally found out that according to this equation 2, 3 times a minus x equals to 2a. We open the brackets on this side of this equation 2, and we found out that 3a minus 3x equals to 2a. We subtracted 2a from this equation 2, and found out that 3a minus 2a is a, so a minus 3x equals to 0. We added 3x to this equation 2, and finally found out that A equals to 3x according to this equation 2. In the next step, complete this right triangle QBC in the new page and implement the Pythagoras theorem. This right triangle QBC. According to the Pythagoras theorem, any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle QBC that occurs from the original drawing. In this right triangle QBC, according to the Pythagoras theorem, QC squared, that is the square of the hypotenuse, equals to QB squared plus BC squared. QC is 3, therefore QC squared is 3 squared, this is 9, and it is equal to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is 8, therefore BC squared is a squared. So in total, according to equation 3, I shall found out that 9 equals to x squared plus a squared. This is according to equation 3, but according to equation 1, we have already found out that a equals to 3x. If a equals to 3x, it means that a squared equals to 3x squared. Therefore, we can substitute a squared this equation 3 by 3x squared for this equation 2. We did it, and we found out that 9 equals to x squared plus a squared, and a squared is 3x squared according to equation 2. So in total, we found out that 9 equals to x squared plus 3x squared. 3x squared is 9x squared. So in total, we found out that 9 equals to x squared plus 9x squared. X squared plus 9x squared is 10x squared, so in total we found out that according to this equation 3, 9 equals to 10x squared. Here we divided this equation 3 by 10, and finally found out that x squared equals to 9 tenths. We took out of this equation 3, and finally found out that according to this equation 3, x equals to the square root of 9, that is 3, over the square root of 10 units in its length. Again, the value of x, that is actually QB, is equal to 3 over the square root of 10 units in its length. This is according to equation 3. According to equation 2, we have already found out that a equals to 3x. So a equals to 3x, and x is 3 over the square root of 10. So in total, a equals to 3 times 3, that is 9 over the square root of 10. So a, that is one side of square ABCD, is equal to 9 over the square root of 10 units in its length. So this is side DC, that is equals to a, and a equals to 9 over the square root of 10 units in its length. Okay. According to equation 1, we have already found out that AP equals to 2/3 x. So AP equals to 2/3 x. AP equals to 2/3 x, and x equals to 3 over the square root of 10. So in total, AP equals to, here we have 3 in the numerator and 3 in the denominator, so 3 will be cancelled, and we left only with 2 over the square root of 10. So in total, we found out that AP equals to 2 over the square root of 10 units in its length. This is AP, is equals to 10 over the square root of 10. Again, AP equals to 2 over the square root of 10 units in its length. What is the ref of PD? From the moment it is very easy to say that PD in total equals to AD minus AP. PD equals to AD minus AP. So PD equals to AD. AD is A, and A equals to 9 over the square root of 10 minus AP. AP equals to 2 over the square root of 10 units in its length. And so in total, we can find out that PD equals to 9 over the square root of 10 minus 2 over the square root of 10, that is 7 over the square root of 10 units. This is 9 segment PD, that is equal to 7 over the square root of 10 units in its length. In the next step, we join points P and C together by straight line. By joining points P and C, we created here two right triangles. We created the right triangle PDC, and we also created the right triangle PQC. Because of the fact that the green shape consists exactly those two right triangles, it means that the area of the green shape must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this right triangle PDC plus the area of this right triangle PQC. So repeat again, we found out that the area of the green shape in total equals to the area of the right triangle PDC plus the area of the right triangle PQC. The area of the right triangle PDC is equal to the base, that is PD, times the height, that is DC, over 2. The area the area of the right triangle PQC is equal to the base, that is PQ, times the height, that is QC, over 2. Again, the area of the right triangle PQC equals to PC times CC over 2. The area of the right triangle PQC equals to PQ times QC over 2. PC is 7 over square root of 10, DC is 9 over square root of 10 divided by 2. PQ is 2, QC is 3 divided by 2. What is the value of this expression? 7 times 9 is 63, square root of 10 times square root of 10 is 10 divided by 2. Here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and left only with 3. 63 over 10 over 2 equals to 63 over 10 times 2 plus 3. 10 times 2 is 20, so in total this expression equals to 63 over 20 plus 3. Here we multiply 3 by 20 and then we divide it by 20 in order to become factor of this number. So in the numerator, in total we have 63 plus 20 times 3, that is 60, divided by 20. 63 plus 60. 63 plus 60 divided by 20. 63 plus 60 is 123 over 20. 123 over 20 is 6.15. So in total, we should find out the area of this green shape equals to either 123 over 20 square units, or in terms of numbers, the area of this green shape equals to 6.15 square units. So we finish with the first question. And the next time I actually present it to the second question, and we solve the second question in this lecture. In the second question, our mission is to find out the area of this green shape. So in the drawing we have quarter circle AOB. Those three angles, they're all right angles, and OB equals to 5, that is to say the radius of this quarter circle is 5. In addition, we know that arc AP equals to arc PQ equals to arc QB. Our mission is to find out the area of this green shape. So first of all, we join points O and C together, O and P together by straight line. We also join points O and Q together by straight line. Because of the fact that arc AP equals to arc PQ equals to arc QB, we can implement here rule 20. So we put here rule 20. According to rule 20, in front of equal arcs, there are equal center angles. So in the drawing we have a circle, and we know that arc AB equals to arc CD. According to this rule 20, here in front of arc AB we have angle alpha, in front of arc CD we have center angle beta. In front of arc AB we have center angle alpha, and in front of this arc CD we have center angle beta. And according to this rule 20, the two center angles are equal to each other. That is to say, center angle alpha equals to center angle beta, because of the fact that those two center angles are located in front of those two equal arcs that are equal to each other. Okay, so we can actually implement rule 20 in our drawing. In our drawing, we have arc AP that is equal to arc PQ, that is equal to arc QB. In front of arc AP we have center angle AOP. In front of arc PQ we have center angle POQ. In front of arc QB we have center angle QOB. And because of the fact that those two center angles, that is to say AOP, POQ and QOB, they are all located in front of equal arcs, they must be also equal to each other. So if one center angle is x, then the other center angles must be also equal to x. So x plus x plus x, the sum of those three center angles, is very easy to see that the sum of those three center angles is equal to angle AOB. But angle AOB equals to 90 degrees, therefore the sum of those three center angles must be also equal to 90 degrees. So 90 degrees equals to 3x. We divided the equation by 3 and finally found out that x equals to 90 degrees over 3, 30 degrees. So set triangle AOP equals to 30 degrees in size, set triangle POQ equals to 30 degrees in size, and set triangle QOB also equals to 30 degrees in size. In the right triangle MPO, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 60 degrees, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. Likewise, in the right triangle NOQ, this big angle NOQ equals to 60 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 30 degrees, according to the sum rule that says that the sum of the angles in a triangle is equal to 180 degrees. OP is the radius of the quarter circle, that is 5. OQ is also the radius of the quarter circle, that is equals to 5. In the next step, I copy the right triangle MPO, this right triangle NOQ in equation. I should prove that those two right triangles can join to each other according to angle side angle rule. So okay, those are the two right triangles that are correct from the original drawing. This is triangle MPO, this is triangle NOQ. So what those two right triangles can go into each other? First of all, those two angles are both equal to 60 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 30 degrees and therefore they are equal to each other. And finally, side PO equals to side QO. They are both the area of the circle, that is equals to 5 and therefore they are equal to each other. So I can prove that those two angles and the side that is included between those two angles, that is side OQ and the right triangle MPO, are correspondingly equal to those two angles and the side that is included between those two angles, that is side QO in the right triangle MQO. And therefore those two right triangles can go into each other according to angle side angle rule. And for the fact that those two right triangles can go into each other, we will derive that they have also the same areas. Well, because any right triangles and any triangles that can go into each other, they must have also the same area. So the right triangle MPO is equal to the area of this triangle MQO. Repeat again, according to equation 1, the area of triangle MPO is equal to the area of triangle NQO, the right triangle NQO. But because of the fact that triangle MPO consists of this quadrilateral MNPS and this right triangle NOS, it means that the area of this triangle must be equal to the sum of the two areas, the sum of the areas of the two components that it consists of. That is to say, the area of this triangle MPO must be equal to the area of this quadrilateral MNSP plus the area of this right triangle NSO. So I repeat again, the area of the right triangle MPO is equal to the area of quadrilateral MNSP plus the area of the right triangle NSO. And according to equation 1, the area of triangle MPO equals to the area of triangle MQO. So here, this is triangle NQO. This triangle NQO consists of this right triangle NSO and this right triangle SQO. And therefore the area of triangle NQO, the mixed triangle NQO, must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this right triangle NSO plus the area of this triangle SQO. So I repeat again, the area of triangle SQO must be equal to the area of the small right triangle NSO plus the area of triangle SQO. Here, the area of triangle NSO, both sides of this equation 1. So we subtracted the area of triangle NSO from both sides of the equation, so the area of triangle NSO will get cancelled, and we left only with the area of quadrilateral MNSP is equals to the area of triangle SQO. Okay. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area is very easy to see from the drawing that the area of the green shape equals to the area of this green quadrilateral MNSP plus the area of this small shape PSQ. Okay, again, the area of the green shape in total equals to the area of quadrilateral MNSP plus the area of the small shape PSQ. But we have already found out the area of quadrilateral MNSP is equal to the area of triangle OSQ. Therefore, we can substitute the area of quadrilateral MNSP by the area of triangle OSQ. We did it, and we found out that the area of the green shape equals to the area of quadrilateral MNSP is the area of triangle OSQ plus the area of the small shape PSQ. So in total, we found out the area of this green shape, that is the area that we are looking for in this question, is equals to the area of this triangle SOQ plus the area of this small shape PSQ. But the area of the small shape PSQ plus the area of triangle OSQ is equals exactly to the area of sector POQ. Okay. And again, the area of triangle OSQ plus the area of the small shape PSQ is equal to the area of sector PSQ or OPQ. Again, the area of triangle OSQ plus the area of the small shape PSQ equals to the area of sector PSQ. So the area of sector OPQ. This is sector OPQ. But what is the area of the sector OPQ? It is equal to pi r squared. It is the area of the circle that contains the sector times the angle between the legs of the sector, that is 30 degrees over 360 degrees. And again, the area of sector OPQ is equal to pi r squared. It is the area of the circle that contains the sector times the angle between the legs of the sector, that is 30 degrees over 360 degrees. R is 5, therefore r squared is 25. Therefore, in total, this expression equals to 25 pi. 30 degrees over 360 degrees is 1 over 12. So in total, this expression equals to 25 pi over 12. 25 pi over 12 is 6.545. So in total, we found out the area of this green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape equals to 6.545 square units. Okay? Thank you very much.